Dear students, in this module, we will be able to learn about carboranes as ligands, about the formation of carborane anions, and about the complexes of transition metals and F-block elements with carboranes. There is an intrinsic property of carboranes whose significance and potential are so far-reaching that it impacts virtually every field of chemistry. The carboranes have shown extraordinary ability to accommodate metal and non-metal atoms in their cage framework. Let us explore how these carboranes as ligands. The most extensively studied carboranes are 1,2-dicarba-dodecaborane and its substituted derivatives. One of the intriguing properties of 1,2-dicarba-dodecaborane is being the most accessible starting material and its ability to isomerize thermally. It rearranges to 1,7-dicarba-dodecaborane at 450 degrees Celsius and is expected to be more stable since the relatively positive carbon atoms are more separated from each other. The closo 1,2 and 1,7-dicarba-dodecaboranes and their C-substituted derivatives are degraded quantitatively by the base such as alkoxide ion to give isomeric nidocarborane anions such as C2B9H11-. The alkoxide ion attack produces only C2B9H12-, while the use of very strong bases readily acquires H+ to give C2B9H12-, which can be protonated to form a neutral nidocarborane C2B9H13, which are strong acids and upon heating give another closocarborane C2B9H11 with loss of a molecule of hydrogen, as shown in the equilibrium reaction. The isomeric C2B9H12- ion upon treating with anhydrous acids followed by heating are converted into closocarborane C2B9H11 in high yields, as shown in the reaction. The removal of BH2+ unit from C2B10H12 may be interpreted as a nucleophilic attack at the most electron deficient boron atom of the carboranes. Molecular orbital calculations have shown that the carbon atoms in carboranes have considerable electron withdrawing power. Thus, the most electron deficient boron atoms are those which are adjacent to these carbons. These will be in position 3 and 6 in 1,2 C2B10H12 and at position 2 and 3 in 1,7 C2B10H12. Hathron in 1964 has demonstrated that the open pentagonal faces of C2B9H11-2- bear a strong resemblance structurally as well as electronically to the cyclopentadienyl anion C5H5-, which forms very strong bonds with the transition metals exhibiting the geometry. As you can see in the figure, the metal atom is bonded to the pi electron cloud of cyclopentadienyl anion. The anionic carboranes can act as ligands towards metals in the same manner resembling that of cyclic organic ligands. For example, the nidocarboranes of the formula C2B9H11-2- have p orbital lobes pointing towards the missing site of the icosahedron, as shown in the figure. This arrangement of p orbitals can be compared with that of the p orbitals of cyclopentadienyl ring, as shown in the figure. The trivial name dicarbolide ion has been proposed for C2B9H11 2- ion, which is derived from the Spanish word olla, meaning a pot. With a view of the shape of this 11-particle icosahedral fragment, the hypothetical parent olide ion would then be B11H11 4-. Let us see the transition metal complexes and F-block metal complexes of these carboranes. The dicarbolide ions combine readily with transition metal complexes such as iron 2+ or cobalt 3+, having both the D6 configurations, thus leading to bis dicarbolide Fe2 and bis dicarbolide cobalt plus respectively. Isoelectronic with the sandwich complexes of cyclopentadienyl ion with iron and cobalt, known as ferrocene and cobaltocenium ion respectively. The iron complex undergoes reversible oxidation analogous to that of ferrocene. The structures of these bis dicarbolide metal complexes systems are usually having essentially D5D symmetry as shown in figure A, if the difference between the boron and the carbon atoms is ignored. In case of bis dicarbolide copper 2- and bis dicarbolide copper- species and probably some other, there is a slippage of ligands as shown in figure B. As you can see in the figure, the two ligands are displaced or slipped away from the axis. This is caused by the presence of too many electrons to be accommodated in the bonding molecular orbitals of the symmetrical structure. The mixed ligand complexes containing one dicarbolide ligand and some other ligands or set of ligands, for example cyclopentadienyl anion or PH4C4 or 3 carbonyls, are known besides the bis dicarbolide metal complexes species as shown in the figure. In figure A, you can see this mixed complexes contains one dicarbolide ligand and the other one is cyclopentadienyl anion. In figure B, you can see there is one dicarbolide ligand and the other one is PH4C4 ligand. And in figure C, one of the ligand is dicarbolide and the other one are 3 carbonyls. The majority of the compounds made from carbolide ions contain the isomer with adjacent carbon atoms, that is 1,2 carboranes. However, isomers obtainable from 1,7 carboranes with non-adjacent carbon atoms are also known. The reaction of cobalt chloride with carborane anion leads to the reaction wherein monocarbolide cobalt ion complex is formed. This reaction, when carried out at room temperature, yields red anionic complex, whereas when the reaction mixture is refluxed in 1,2-dimethoxyethane, the product is brown. Similar reactions occur with other transition metals. The figure shows the structures of these isomeric species. It can be seen that the brown isomer is in fact a mixture of geometric isomers. The comparison of figure A with figure C reveals that the red isomer is derived directly from the skeleton of C2B7H13, whereas the brown isomer contains ligands with a rearranged skeleton. Both the red and the brown forms rearrange upon heating at 315 degrees Celsius for 24 hours quantitatively to an orange isomer exhibiting structure shown in figure D. In view of the shoe-like shape of this C2B7H9 2- ions, a trivial name based on the Spanish word for shoe, zapato, has been assigned. Thus, the hypothetical borane ion would be B9H9 4-, which would be called zapide ion, and the corresponding carborane C2B7H9 2- would then be called dicarbazapide ion. Thus, the following ion is called bis dicarbazapyl cobalt 3 ion. As shown in the figure, A is the nidocarborane C2B7H13. In the figure B, the two brown isomers of C2B7H9 whole twice CO, and in figure C, the red isomer of C2B7H9 whole twice CO, and the thermally most stable isomer of C2B7H9 CO-. Now, the F block metal complexes with carboranes. The complexes of F block elements derived from carborane ligands are also known, as shown in the figure. The direct salt metathesis reaction between the carborane shown here and lanthanum chloride in THF yields full sandwich lanthacarborane as shown in figure A. The average lanthanum cage atom distance is 280.4 picometers and the ring centroid angle is 132.7 degrees. The structure of Samara carborane shown in figure B shows that samarium 3+ ion is surrounded by an eta 5 cyclopentadienyl ring, an eta 6 hexagonal C2B4 face of C2B10H11 cage, and the two THF molecules in a distorted tetrahedral manner. The ring centroid samarium ring centroid angle is 125.1 degrees, and average samarium cage atom and samarium carbon distances are 280.3 and 270.6 picometers respectively. Figure C shows the coordination environment of erbium atom in the following complex. The erbium atom is coordinated by eta 7 arachno C6H5 CH2 whole twice C2B10H10 4- and sigma bonded to two BH groups from a neighboring arachnocarborane ligand and one THF molecule. The average erbium boron cage distance is 266.5 picometers, and that for the erbium carbon cage is 236.6 picometers. The actina carborane bearing eta 6 C2B10H12 2- ligand formed by the reaction of OC2B10H12 with excess of potassium metal in THF leads to the formation of the carborane upon treatment with a THF suspension of uranium chloride, wherein each uranium 4+ ion is bonded to eta 6 nidocarborane and eta 7 arachnocarborane and coordinated by two BH groups from the C2B5 bonding phase of a neighboring arachnocarborane ligand. So this is all about the transition metal complexes and the lanthanide complexes of carboranes. Now let us summarize what we have learned. Carboranes can act as a very effective polyhaptoligands to form metallocarboranes. The icosahedra carborane cage C2B10H12 can be converted to nido C2B9H11 2- and nido C2B10H12 2- or arachno C2B10H12 4- anions. The nido C2B9H11 2-, that is nido dicarbolide, has a planar 5-membered C2b3 ring with delocalized pi orbitals similar to that of cyclopentadienyl ring, indicating thereby that dicarbonate ion can act as an eta 5 coordinated ligand to form sandwich complexes with metal atoms analogous to that of metallocenes. The nido C2b9H12 has nearly planar C2b4 6-membered ring and delocalized pi orbitals analogous to benzene and may function as eta 6 ligands. The arachno C2b10H12 has a boat-like C2b5 bonding phase in which the 5 boron atoms are coplanar and the 2 carbon atoms lie approximately 60 picometers above this plane.